Hi everyone, so hope you're all doing well. So today's video is really going to be aimed at those of you going into year 13 in September, so next month starting year 13. So I found this Edexcel AS first year A-level pure maths paper, and I found this question at the end, this question 14, which is a good proof question, which I feel would be a good question to go through to prepare you for next year. So we're going to do that today.
But before we get into today's video, please do make sure you do click like and click subscribe. Click that like button, click subscribe. It really helps me out and it's free. It doesn't cost you anything and it takes you less than a second. So please do click those buttons and we'll get into today's video now.
There's this question here, this question 14, which is the proof question, which I think would be a good question to look at. And I think if we can do this question here, then it would be good preparation for the new kind of proof that you'll be doing in year 13, because you'll be learning new things like by proof by contradiction, which is kind of what you learn in year 13. So this would be good preparation for that. It's not proof by contradiction, this question, but it's good preparation for the kind of proof you may be doing or you will be doing in year 13. So question 14, so part one says this. So a student states that if x squared is greater than 9, then x must be greater than 3. So we want to determine whether or not this statement is true, giving a reason. Okay, so in this question here, the student is assuming that x squared is greater than 9. So we want to assume, so we're going to assume that x squared is greater than 9. And assuming that, the question essentially is saying, if we assume that x squared is greater than 9, is it true that x must be greater than 3? So there's a couple ways we could approach this one. I guess the kind of way that I would think about this one is by thinking about this graphically. So we've kind of got here, I mean, we have got here, not kind of, we have got here a quadratic inequality, haven't we? So we've got a quadratic inequality in the variable x, because we've got x squared, which is our quadratic term, is greater than 9. So I guess one way you could approach this one, again, there's a couple ways you could approach this, but one way we could approach this is by sketching sketching two lines, two curves. So we could sketch the curve y equals x squared, and we could compare that with the curve y equals 9, since we've got x squared there, and we've got the number 9 there. So let's do that. So let's sketch our curve y equals x squared, and let's sketch our straight line y equals 9. So y equals x squared is our usual quadratic curve looking like that. And y equals 9 is a horizontal flat line when the y coordinate on your axes is equal to 9. So it's just a flat horizontal line like that. Y equals 9 because all of the y coordinates on this curve are equal to 9. Okay, so then, sorry, on that line, sorry, not curve. So now then, the question wants us to assume that x squared is greater than 9. So in other words, we look at our two lines, so this curved line, I'll do this curved line actually in blue, this x squared line in blue, darker kind of blue, and I'll keep the horizontal y equals 9 line in black. So when is the blue line greater than the black line? So remember, we want x squared to be greater than 9. So when is x squared greater than 9? So when is the curve greater than the black line? So we can see we've got 2 points of intersection there. We just dot those down and dot those down. We can see that the curve is greater than the black line when we've got y values to the left of this point of intersection. Sorry, x values to the left of that point of intersection. And also when we've got x values to the right of that point of intersection there, we can see that the curve, the blue line, is above. So this curve is above the black line, the black flat line for these sets of x values. So what is this point of intersection? What are the x coordinates of this point of intersection? So that's going to be 3 there. That coordinate is going to be 3. And that x coordinate there is going to be -3. So why is that true? Well, it's true because we know that 3 squared, so substitute x equals 3 into that formula there. 3 squared is 9, so the y value is 9. So that matches up with the line y equals 9, this horizontal line y equals 9, doesn't it? And the same with this here. So when x is -3 all squared is 9. So therefore, again, it does completely match up. Okay, so we know that if x is greater than 3, so let's just write this down here then. So if x is greater than 3, then x squared is greater than 9. And also from this kind of region down here, so if x is less than -3, then x squared is greater than 9. So what we can conclude from this graph is that if x squared is greater than 9, then it means that either x is greater than 3 or x is less than -3. Okay, so either x is greater than 3 or it's less than -3. Now, let's go back to the statement. So the student says, if x squared is greater than 9, then x must be greater than 3. Is that true? No, it's not true, because we just said down here, didn't we? If x squared is greater than 9, either x is greater than 3, so this part here, or x is less than -3, so this part down here. So it's either or. So it's not x must be greater than 3. X could be greater than 3, or it could be less than -3. So therefore, we just want to say the student is incorrect. So therefore, student is incorrect. So we could do a graphical analysis like this. I mean, it is only a 1-mark question, to be fair. So you could just pick a counterexample with this one. So you could just do a proof by counterexample. You could just say, let x be equal to -5. Then that means that x squared is equal to -5 all squared. And -5 all squared is 25. And 25 is greater than 3, isn't it? Obviously, 25 is greater than 3. So x squared is not greater than 9 because -5. Sorry, let me repeat that again. X squared is greater than 9. Sorry, this should be again 9, not 3. I made a mistake here. Sorry. So x squared is greater than 9 in this case. But was x greater than 3? No, because x was -5. X was actually less than. It was less than 3. So when x is less than 3, there are actually x values which give you x squared values greater than 9, as we just see in this example there. So you could use a proof by counter example. That would be fine as well. So you could use a counter example proof instead of this graphical analysis with this question. But I think personally it's good practice to get used to doing these graphical analysis, this kind of graphical analysis, especially with these inequality questions, these quadratic inequalities, because when you solve quadratic inequalities, I do recommend to do graphical analysis, this kind of graphical stuff here. Okay, great. So let's go to the next part of the question, part 2. So part 2 of the question. So this says, prove that for all positive integers m, n cubed plus 3n squared plus 2n is divisible by 6. So I guess the first thing to realize is that n is a positive whole number, so it's a positive integer, so it's a positive whole number. We could also use set notation to write this. We could say that n belongs to the set of positive integers. So we could use that notation as well. So in second year, sometimes they do tend to use this notation. So if you've not seen this notation before, I'll just write this down here. So this kind of C with a line in the middle, like a kind of curly E, just means belongs to. So it's just mathematical notation for belongs to dot, dot, dot. And this Z notation is the set of integers, set of integers. So a Z plus is just the positive integers, so set of positive integers. Okay, so when we say, so like what I said there, so n set of positive integers, this just means, so if we translate that into English, it just means that n is a positive integer. So n belongs to the set of positive integers is kind of what that's reading there. If we translate that like symbol for symbol into English, so n is a positive integer. So again, you may use this kind of notation, and you definitely will use this kind of notation a lot in second year. So we want to prove that this n cubed plus 3n squared plus 2n is divisible by 6. I'm just going to write this down here. So we want to prove, so WTP just means want to prove that n cubed plus, I think it was a 3n squared, yeah, n cubed plus 3n squared plus 2n is divisible by 6, which just means it's a multiple of 6. So we want to prove that it's a multiple of 6. So how are we going to do this? I mean, normally with proof questions that we see at GCSE, for example, normally what we can do, I'll just do this in a box here, is normally we may have something like, 6n squared plus 12m. Well, if we just factorize out of 6, we get 6 times n squared plus 2n. So we can just say, well, 6 times any whole number is multiple of 6. So this is definitely going to be a multiple of 6. So that's normally what you get like at GCSE. Now, with this question here, if we look at that expression here, there are literally no multiples of 6 in those three terms. So we've got an n cubed term here, an n cubed term here. So that's an n cubed term. There's no multiple of 6 there. We can't see a number 6 there. We've got a 3n squared term there. I mean, 3 is a factor of 6, but it's not a multiple of 6, is it? And the same with this 2 there. So we got 2, a factor of 6, but not a multiple. So we can't factorize out a 6 at all. So we can't do this kind of GCSE kind of proof of this question. So with these kind of questions where we can't see an obvious way to start, the recommendation I have is to try and factorize it first. So step 1, can we factorize? Step 1, can we factorize? So hopefully you'll be able to notice that we can factorize. Yes, we can. We can actually factorize out an n from all of these three terms. So you've got n cubed plus 3n squared plus, sorry, that should be a 2 plus a 2m. We can actually just factorize out an n. Just get n times by n squared plus 3n plus 2. Now, can we factorize even further? So we want to factorize as far as possible with these expressions. Yes, we actually can. So if we look at what we've got here, this quadratic factor, we've got this n times by this quadratic factor. We can actually factorize that quadratic. So if we put an n in there and an n in there, can we think of two numbers that times together to make 2, but add together to make 1? Sorry, to add together to make this 3 there, this coefficient of 3 there. Yes, we can actually, yeah, 1 and 2. So we put a plus 1 there, plus 2 there. So now we fully factorize this cubic expression. Now, how is that useful? So hopefully, looking at this expression here, you're able to notice that we've got 3 consecutive numbers. We've got 3 numbers there, n plus 1, n plus 2. So we've got 3 consecutive positive integers. So let's just make a note of this here. 3 consecutive positive integers. So this expression is the product of 3 consecutive integers. So essentially what we're trying to do here is prove that the product of 3 consecutive integers is a multiple of 6. Now, how can we do this? We've got 3 whole numbers in a row, essentially. So let's think about some facts then. Let's write down some facts that we must know about these numbers. So we've got 3 consecutive numbers. So we've got 3 consecutive numbers, 3 consecutive whole numbers, positive whole numbers. Now, I guarantee you that at least one of them, so at least one of these 3 numbers, so at least one of these 3 numbers is even. Now, how can I guarantee that to you? So how I can guarantee this to you is by this. So pick any 3 numbers, consecutive numbers you like. So for example, you could pick, well, you could put 1, 2, 3. You could also pick, I don't know, 77, 78, 79. You could also pick, I don't know, like 62, 63, 64. So pick any 3 consecutive integers in a row. Now, what do you notice? Well, regardless of which 3 numbers you pick, one of them or 2 of them will be even. So with this first example there, that's even. With this second example there, that's even. With this example, this last one, we got 2 even numbers there. So it's quite obvious that when you pick 3 numbers in a row, one of them, at least one of them is going to be even. So why is that important? So if you pick 3 numbers, 3 consecutive numbers that appear in a row, right? At least one of them is going to be even. It means that when you times those 3 numbers together, you're going to get an even number. So what we can say from here then, what we conclude from here, sorry, I'll just turn this alarm off. So what we can conclude from here, what we can conclude is that when we times together 3 numbers, 3 consecutive numbers, right, it means that the product must be even because at least one of these numbers is even. So we know, so let's just make this really clear. So we know that when we do an even number, so even number times by any integer, well, any positive integer, I'll just put positive here. So any even number times by any positive integer, that's going to be an even number. Okay, that's just a fact, right? Pick an even number, pick a multiple of 2. times it by any positive whole number, it's going to be even. It's going to be in the 2 times tables. So therefore, what we can say is we can say that n times n plus 1 times n plus 2 is an even number. It's definitely going to be an even number. So in other words, it's a multiple of 2. So it must be a multiple of 2. So we know for a fact it's a multiple of 2. And again, it's because one of these 3 numbers must be even, at least one of them. So it could be 2, but it could be 1 as well. Again, when you times an even number by any number you like, it's going to be even. So I know that this is going to be even. I know it's going to be a multiple of 2. Okay, so we know that. Now, what else do we know about these 3 consecutive numbers that we're timesing together? So we know that at least one of them is going to be even, but we also know, so we know that one of these 3 numbers is a multiple of 3. So we know that one of them is in the 3 times tables. Now, how do we know that? So again, hopefully it should be quite obvious to you. If you pick 3 random numbers, so for example, 3 random numbers in a row, so like, 12, 13, 14, I guarantee you that regardless of what 3 numbers you pick, consecutive 3 numbers you pick, one of them exactly is a multiple of 3. So in this example here, it's 12, right? Now, how do we know that? Because the 3 times tables, multiples of 3, let's think about our 3 times tables, 3, 6, 9, sorry, that should be a 9 there, 3, 6, 9, 12, so on and so on and so on. Multiples of 3 appear after every 3 numbers. So after every 3 positive integers, you get a multiple of 3. So if you pick 3 consecutive integers, one of them is definitely going to be multiple of 3, just because of the fact that multiples of 3 occur every 3 integers. So if you pick 3 random integers in a row, one of them is definitely a multiple of 3. So therefore, we know that either n plus 1, n plus 2 is a multiple of 3. Now, again, similar to this kind of analysis we talked about here, that when we do an even number times by any positive integer, we get an even number. So when we do, so we'll write this here, so we know that when we do a multiple of 3, so pick a number in the 3 times tables, pick any number you like in the 3 times tables, times it by any random positive integer you like, so any positive integer, what do you get? You get a number in the 3 times table. So you get, again, another multiple of 3. Okay, so again, pick a multiple of 3, pick, 12, times it by any number, 17. It's definitely going to be in the 3 times tables. Why? Because 12 is in the 3 times tables. So if 12 is in the 3 times tables and you're timesing it by another number, you're getting 3 times a random number. It's going to be in the 3 times tables. So it's definitely going to be a multiple of 3. So let's write this here. So multiple of 3. So therefore, that means that n times n plus 1 times n plus 2 is a multiple of 3. So it's a multiple of 3. And as we said before, it's even. It's a multiple of 2. It's a multiple of 2. So therefore, we've got this number here, n times n plus 1 times n plus 2. It's even, multiple 2. It's also multiple 3. So therefore, it must be, I should say, so it must be a multiple of 2 times 3, which is equal to 6. So it must be a multiple of 6, right? So again, think about it. You've got an even number, and it's a multiple of 3. It must be a multiple of 6, right? So it must be. So therefore, that's how we would prove that result there. So you can prove that result just by factorizing, and then realizing you've got the product of 3 consecutive integers. We know one of them is going to be even, so it's going to be even. And we know one of them is going to, at least one of them is going to be even, I should say. And we know that one of them must be a multiple of 3. So therefore, your final answer will be a multiple of 6. Now, it was only a 3-mark question, so we don't have to go into this really detailed analysis that I've done here. You can just, factorize your expression and say, we know we've got 3 consecutive positive integers, so that's key here. You do want to mention this in your answer, but you don't need to go into all these explanations and all these examples that I've done here. You can just say, well, at least one of them is going to be even, one of them is going to be a multiple of 3, so therefore 2 times 3 is 6. It's a multiple of 6, so you can just do that. You don't have to do this explanation here. I just wanted to go through it so you can actually see where that comes from. So hopefully that was useful, and it's good to get a good head start with some proof questions before you go into year 13, because you will be doing some more proof in year 13. So it's good practice to get you ready for year 13. So yeah, hopefully that was useful. Please do drop a comment if you do have any questions on this, or you do want some further clarification on anything in that question today.
If you are interested in having an online maths tutor for either A-level maths or GCSE maths, please do email me, because I am available to help out. So my email is doctordifferentiation@gmail.com. So just drop me an email, just drop me some details about you, whether you're doing A-level maths, GCSE maths, and if there's any specific areas of maths that you need help with. So drop me an email, or get your parents to drop me an email, and then we can discuss everything about price, etc. So drop me an email and we can get sessions booked in.